Okay, let's get started. So good morning, everyone. I'm Patrick Griffiths from ESA, and I'm co-hosting this side event workshop with Steffen Fritz from IASA, who's online. Okay, so good to see the list of attendees here, and thanks everyone for tuning in. We have a couple of participants that will join a little bit later because they're coming from the US, but we also have participants from China, from the East, so that's great. And we have a quite packed agenda today for this workshop on training and reference data for AI and machine learning in Earth observation. So the first part of the talks that we have scheduled are basically looking at new tools and methods. We have contributions from EarthPulse, IASA, FAO, JRC, and from the ESA World Serial Project. And then we would basically do a little break. Let's see how much time we have. And then the second part would look at more the larger community initiatives, where we have one contribution on the Aereo project and with the new OGC working group on training data markup language. Then hopefully an update on the Lacuna Fund and some best practices on validation procedures and protocols. And then an update also from Radiant Earth towards the end of the workshop. We also prepared a couple of polling questions that we would like to put to the audience. Unfortunately, Slido was purchased by an American company and now it's no longer GDPR compliant, so we cannot use it anymore. But Sarah, who's assisting us, was able to find an alternative that's fully GDPR compliant, so we're going to use that tool. Unfortunately, we have to do this as live polling, so we all have to respond to the questions at the same time. And maybe we do that before the break or right at the end of the entire block of presentations. Okay, but we just wanted to spend a couple of minutes on an introduction here. And I have a few thoughts as an introduction to this thematic workshop from my side. So why do we care about this topic of training data and reference data? So from my perspective, you know, we are in this golden era of Earth observation where we have plentiful of data archives, you know, with unprecedented temporal resolution, great spectral resolution, dense SAR time series, commercial data. All of that is available to us in, you know, in increasingly efficient and convenient ways. But at the same time, there is this training and reference data bottleneck, you know, and it's of course primarily for machine learning applications, but also for validation and calibration of other models and results. It's a really pity. And, you know, the biggest aspects of this bottleneck are the limited availability in general, which also links back to the willingness to share training data sets. They are often very, you know, you have to put a lot of manual labor in to create them, but there, you know, probably exists quite a good amount of valuable training data that no one really shares. So the willingness to share is one aspect. But also it's a little bit limited in terms of the application areas. You know, you probably find a lot on land cover and crop mapping, but things like yield or pests or, you know, bark beetle infestion might be much lower, you know, and there might be much less available of that. So then there's also this aspect of limited discoverability, accessibility, interoperability, and, you know, this links back to fair data principles for training data, which is something I think that we should all think about, even though it's maybe less of a pressing issue. And then there's also a lack of quality control and best practices. And we have in Earth observation, you know, established quality control procedures for the Earth observation data, but for the, you know, the training reference data, validation data, there is no such thing, at least in the kind of in the application and land community. And then there are a couple of Earth observation specific challenges, you know, that you know, that there's just as I mentioned before, there's a limited diversity in the available training and reference data sets, you know, and also there's currently kind of too much focus, in my opinion, on computer vision applications. It's not all computer vision. You know, in Earth observation data, ground campaign, the data collected in ground campaigns are as important and valuable as, you know, computer vision training data for object detection. It's just one application. And currently there's a little bit too much focus on deep learning and stuff like that. So, and then also the other aspect is, you know, this making legacy data available. You know, in so many research labs, there's plenty of good reference data, validation data, training data that could be used, but it needs to be kind of polished and brought into a format that, or a form, not a format, that we can all use it in a consistent way. Okay, these are just some introductory thoughts, and I wanted to make one announcement, and that is that we're currently preparing a new tender at ESA IOP on a training dataset platform. So this is going to be a competitive tender to be published within this year, a 1.2 million budget provided over 3 years. And the activity will cover the design and implementation, operation, maintenance, and evolution of the platform. And we're looking for a consortium with strong expertise in Earth observation science, machine learning, cloud, ICT, and service provisioning, and some data science. And in a nutshell, the elements that, it's still in the phase of design, the tender, but the elements that are definitely going to be in there, there's a central interconnected repository and curation mechanism for training data, reference data, for trained models, for benchmark data sets, including versioning and provenance. There should be a whole set of data engineering tools, open data engineering tools for creating and optimizing training and reference data sets, including kind of a marketplace mechanism so that we can offer third parties to onboard their relevant applications into this platform. There should be some dedicated resources for efficient training of models and validation protocols, executing validation protocols. Should be interconnected with our Earth observation platform resources, provide some capabilities for EO feature engineering, and ingestion, quality control, and curation of legacy data sets plays a role. And then really we want the bidders to think about the data population strategy and an incentive for data sharing so that, that you really lead to an increasing onboarding of the data offering. And then final thought here, we're discussing training and reference data today. We did it before a couple of years ago, but I would like to continue this discussion with all of you at the LPS next year in Bonn in May. And there we have a theme called Open Earth Forum, which we set up to basically have a little bit of feedback from the user community if the data engineering tools, the platform tools that we're developing corresponding to the needs of the community. And here we will also have time to organize some Agora forums on the aspect of reference and training data. I hand over to Stefan for some specific thoughts here on the in situ components.
Thanks a lot, Patrick. Some things Patrick has already outlined, but I just wanted to particularly stress again some of the challenges we are currently facing. And as Patrick has already pointed out, there is really insufficient coordination at the moment also to open up existing in situ data. So it's very dispersed and fragmented. And it's a real challenge. Also, the funding for in situ data has been quite limited, where currently the funding is very strongly on machine learning and classifications and data products rather than the actual really important input for those classifiers. Also, when you look at the Copernicus budget, for example, the in situ component is really a small fraction of the overall budget. And as said, a lot of hype is going into AI and ML, machine learning, computer vision. But there is some initial research already which shows that the reference data being used can actually matter more than the classification algorithm you're using. And this is really important because that could shift some attention also more to in situ. And we also know that a lot of in situ data is not shared and more could be shared. And there are many different reasons. And I think we still don't fully understand all the reasons. Some of it is around GDPR, some around this on personal data, also when it's citizens' data, some things you don't want to disclose. But also there are some areas in biodiversity, for example, when there are sensitive species, wildcats or whatever, occurrence data and those things, they are also not shared. Though sometimes it's difficult to understand if some of it is not shared and it's more of an excuse, or if it's real. To understand that is still a challenge for sure. And also, as we know, there is more and more funding now also flowing into the in situ data and making in situ data available, but there are now direct payments for in situ data, and there's the Lacuna Fund, as some of you might know, but also the Commission has realized that more money needs to go into the direct payment for in situ data. And one example is that GeoGLAM, so there is Copernicus for GeoGLAM, where also reference data is being paid for and being then made free and open, and this is in the contract and the tender itself. So these are current new developments we are seeing. And with that, I hand over back to Patrick. Thank you.
Thanks, Stefan. Okay, I think we will get started with the presentations, but just a preview on the challenges that we'd like to open later for the polling. So it's not going to be via Slido, a different tool, but we have a couple of questions here. Just one on which aspects of training reference data require most of our attention right now. Which type of open data engineering tools would you most welcome for working with training and reference data? And some questions just if we should follow a similar model, making European funding available for supporting coordinated collection campaigns, and what type of variables you would like to see covered in such campaigns. And then one last question on how to best incentivize community and industry for sharing of their data sets. Okay, we'll put this link into the chat, and we'll probably do the live polling. Let's see how we get on with time before the break or after the break. Let's see. So back to the agenda, and we'll start with the first talk from Juan Pedro from EarthPulse on their annotation tools. Juan, I think you should be able to take over the. Let me stop sharing.
Okay. I need to give permissions to share the screen.
Matteo, can you please make Juan Pedro and others presenters?
Okay, there could be only one presenter at a time.
I stopped sharing. So.
Yes, I should have given to you.
Can you hear me?
Yes.
Yes.
Okay, my computer is saying that I have to leave the session and go back in because I had to give it permissions to share my screen. So I will be back in 1 minute. Okay, sorry.
Okay. That's weird.
Okay, maybe just as we have a quite full agenda with 11 presentations, we would really ask everyone to stick to a 10-minute timeline, and then maybe if we have time for 2 minutes of questions directly related to the presentation, we'll do that. But we should all stick to 10 minutes for the presenters, please.
I don't know if it helps, Patrick. I could also go now just to win some time.
Yeah, that's what I was thinking. But Juan is back here.
Okay, perfect.
Then now I can share my screen.
That was quick. Very good.
Very good.
I will share my presentation and also the browser because I have a couple of videos I want to show in a demo. I don't know if the sound will be shared also. Do you know that?
I'm not sure. Let's try it out.
Did you hear something?
No.
No?
So
it's not playing, but
yeah.
When
Now
you
it's playing.
if you stop sharing and then start sharing again, there's the possibility to enable sound as well, optimize for sound.
Okay, so I stop sharing and share again. Maybe optimize for movement and video.
Exactly, that option.
Oh, it's asking me to install some audio controllers.
Go.
Maybe we skip that part one. We're a little tight on time.
Okay, no problem. I will play the video and just say the things that I say in the video, but live. Okay, so I start.
Yes, please.
Okay, so my name is Juan. I am the CTO and co-founder of EarthPulse. And well, the title of the presentation is Scan Satellite Collaborative Annotation Tool. This is a labeling tool that we are developing. So I'm very happy that Patrick, you said about this tender because we are building something similar anyway. So we will be looking for it. But I will also talk a little bit about the training data for Earth observation, for AI in Earth observation. What are the challenges that we face and how we approach it at EarthPulse. So first, a very short introduction of our startup. Okay, we are EarthPulse, we are in Barcelona, and our mission is to easier the access to Earth observation data. For that, we use artificial intelligence. Right now, we are mainly focused on assessing impact of floodings and vulnerability of critical assets to climate events. And for that, we use mainly Sentinel-1, Sentinel-2 images, and we use neural networks, combining the outputs of these neural networks with open data to build these indices. So we provide results through our dashboard. This is an example that you can see here for a flooding impact. You can see the flooding masks. These are the outputs of the models. And in the future, we are looking into extending this to also other climate events like fires or volcanic eruptions, like the one happening now in Spain. But in the long run, our objective is to have something like a digital twin Earth, an API where anyone can connect and extract information from Earth observation data without any expertise of this kind of data or artificial intelligence. So during the past year or so, we have been working in this ESA project, the AI Pathfinder. The objective of the project was to identify the current status of deep learning for Earth observation, which are the main barriers that we face nowadays, and also propose these priority development lines in order to overcome these limitations. And among the different conclusions of the project, maybe the data side is the one that it's more interesting for us today. And well, I'm sure that it comes to no surprise, you already mentioned this, Patrick, before, that when we want to train neural networks with Earth observation data, the main problem that we face is the data access. Okay, it's very difficult to access this data, especially for non-Earth observation experts. When I started in this field, it was like very difficult to find this data. Also, depending on the source, if we want high resolution data, it can be very expensive. So the main barrier that the AI practitioners face when they come to our field is this, and also the lack of big and quality annotated data sets. So also working with different data sources can be a little bit of a nightmare because every provider has its own format. So maybe some form of standardization would be very nice. I know that there are some people looking in this field. I also hope to hear from you in the coming talks. So, okay, how to approach this problem at EarthPulse? Here you can see a little bit of a sketch of our main tools that enables us to explore this data, access the data, and prepare our training data sets, and also put them in production. Okay, so as you can see, this is a closed loop of the different tools, so they are interconnected. And here, starting with the SPY, this is our satellite processing application interface that enables us to explore data, access the data. Then we have a scan, that's the thing that I will show you now, which is our data labeling tool. We also have PyTorch. This is an open source library built on top of PyTorch and PyTorch Lightning. We use it for designing neural networks and training them. And finally, we have this models universe, what we call it. It's a model repository where once the models are trained, we put them there, so they are accessible by the different tools. Okay, I think that's it, and I will show you now the demos. Okay, these are a couple of links to videos on YouTube of the demos. I will show you first a demo of a scan, and then I will show you also a demo of how this tool scan and also the models universe is integrated in the library PyTorch. Keep in mind that these tools are under development, so they might change in the future. But if you are interested in them, so just don't hesitate on contact us. So I think the audio is not playing. So oops. Here what you can see is scan. As you can see, it's a web application. Okay, and here on the left we have the different data sets. I put for the demo the Eurosat dataset. It's not the normal Eurosat dataset. This is like a smaller version for us that I use for this kind of demos. And here, instead of classifying images, yes, the video is muted, but if I am muted, it's not, the sound is not being shared. So here are the images. I put 50 images from the Eurosat dataset. And as I was mentioning, for the task of image classification, here when we click the images, we can see the images, of course, and also the different annotations. And here we have 4 different labels, and the annotations are polygons because we are going to build a image segmentation model. And this is an example of how you can annotate with the drawing tools in the platform. And depending on the label that you select, of course, you will make an annotation of this that particular label. You can edit these annotations, you can delete them, of course. And right now we have this polygon drawing tool, but in the future we are planning to add more labeling tools. Okay, when you hit the save button, obviously your annotations are saved. And here in this example, what I want to show is, okay, we have a new image, in this case, without annotations. And if we want to annotate this image, we can, of course, use the drawing tools to make these annotations manually. But since scan is connected with the rest of our tools, it can already use the outputs of a trained model. In this case, I train a model with some of these images, so it would give like a good, nice annotations. So instead of having to drawing them from scratch, you have these AI assisted capabilities where you use another model to provide annotations. In this case, they are already good annotations since the beginning, but imagine that these annotations were not quite good, but they were good enough to save you a lot of time. So instead of having to annotate from scratch, you just hit the predict button, it suggests annotations, and then you just validate these annotations that were suggested. So I think that's it for this demo. And the second demo is the integration with PyTorch. Okay, this is, as I mentioned before, an open source library that we are building on top of PyTorch and PyTorch Lightning, and it's integrated with a scan. So if I go here, okay, here you can see that from PyTorch.io, we have different data sets. We have already integrated common datasets, public datasets. Okay, you can go to the website of the project. It's on GitHub, and you can see ready to use datasets for training models. They are in the examples section. But in this case, we are using the scan dataset, which is a special dataset since it's connected with the scan API, and it can be used to download these images that I just showed you that were labeled. Okay, it's downloading the images. You have some basic information about this dataset. As I was mentioning, it's not the real Eurosat dataset, it's a different version for segmentation. So in this case, you can see the power of these tools. You can make your own datasets very, very easy, very quickly. Okay, some information about the images, in this case is where they are, so we can load them for training. Yeah, here you can see some visualizations of these images. Okay, these are the same images that I was showing you before on scan, and their annotations. These annotations were manually made. Okay, here's a simple UNet model for training with this dataset. Okay, in PyTorch.io, we have these datasets, and also we have implemented different tasks. And in this case, we are going to use the image segmentation task. So we are going to train a model for image segmentation with this dataset that was, as I mentioned before, manually annotated on a scan. And since these tools are connected, it's very easy to just pull the images, pull the annotations, train your model. And in this case, we are seeing some predictions. Okay, I have to mention that these predictions were just, this model was trained on these images, overfit on these images, just to give some good result quickly for demo purposes. And once the model is trained, here the model is exported, okay, in this case using PyTorch torch script. And once this model is exported, you can upload it to the model universe, okay? These are the lines of code that will upload your model to the model universe, and also an example of how you can download this model and use it for, in this case, just checking that the predictions are okay. So what we saw is that with scan, we can label these images. From this library, it's very easy to download these images with the annotations that we made on the platform. And then once the model is trained, we can upload the model into the models universe. And once the model is there, we can use it again with the labeling tool for suggesting new annotations for new images. So this is called active learning, okay? So we are making data sets, training models, using these models to make more data, more labels, easily, quickly, and in this cycle until obviously we hit like our standard metrics. Okay, so that's it. Just a quick summarization of we say. We have obviously these challenges when we have to train especially neural networks with Earth observation data. So, and yeah, this is our solution. We have this active learning cycle with these different tools. Yeah, that's it. Thank you. If you have any questions, and I'm really looking forward to the rest of the sessions to hear what is your approach, your solution to this problem.
Thanks a lot, Pedro. That was a nice demo, and these active learning tools are certainly really interesting for creating training data. I think we have to move on with the second presentation.
Okay.
Yeah, but we have time maybe hopefully later for discussion, and also there's always the chat to for the audience to ask some specific questions. So actually the second speaker is Stefan, who's going to present the initiatives led by IASA, which is GeoWiki, LacoWiki, and Crowd2Train.
Yes, thanks very much, Patrick. You can see the screen, right, and hear me as well?
Yep.
Great, thanks. Yeah, I will try to be fast because we have limited amount of time, but as you know, some of you know, IASA has been involved in the past in developing a lot of in situ based tools, some of it through visual interpretation of very high resolution imagery, that is GeoWiki, but also we've been recently engaging in ground-based data collection tools. So just to flag some of them to you, so Crop Observe, that's actually a recent app we made as part of the eShape project, where you can annotate crops in the field and take pictures of them. There are other tools related to agriculture, or we built one in the Grow Observatory called Grow. And there is another one called AgroTutor, where we specifically give advice to farmers, but at the same time collect crop management data. This is currently being piloted in Mexico. And there are many other tools, and I don't have really time to go too much into detail, but I want to just give you an overview of some of the tools, in particularly GeoWiki, LacoWiki, and also give you a bit of insight in the currently running Crowd2Train project. GeoWiki has been running for the last 12 years, actually. It has been established already initially 2009. And we've been continuously adding new tools to that. Also, we link it to Google Earth Engine, where you can then also get NDVI profiles and so forth. And that, I think, links to the next presentation of Earth Collect. So there are a lot of commonalities to Earth Collect. But also we do very specific targeted campaigns on certain aspects of features we would like to annotate and get information about. Land cover, of course, is a very obvious one. Cropland campaigns we've been running, but also field size, you know, how large are fields globally. And I will now go really, really fast through all the different campaigns which we've been doing. cropland. We've collected many thousands and thousands of validation samples there, with also quite a lot of participants. Field size, we've done a campaign on human impact on forests, always designing particularly targeted appropriate interfaces to collect those specific data sets. Also, we've been validating the global human settlement layer through crowdsourcing, through those campaigns. A very recent campaign we've been doing is on drivers of tropical deforestation, where we really can pin down the driver of the deforestation. Is it pasture? Is it crop? Is it maybe forest management, or is it some natural causes? Very closely linked to this is PicturePile. This is a rapid labeling tool where you just see something, see a picture, and you can just say, you know, is something present? Is there, for example, oil palm visible in the red box? Yes, no, yes, no. And you can be extremely fast in providing massive amounts of training data quite quickly. And this has also been used in the Crowd to Train project. LacoWiki is an open land cover validation tool, which also lets people share data. That's currently used by a lot of European environmental agencies to validate the Copernicus European products, the local components, but also it's going to be used for CLC Plus and other products coming out in Europe particularly. And there's, of course, always the task for national environmental agencies to provide feedback and to do a in-country validation of those European products. And LacoWiki has been recommended to do that, and it's still being used, though we are still looking for continuous funding because we need to really maintain and update the platform. But just very briefly, it lets you upload your data set. It's very broad. You can upload any data set you want to validate, any map in any region of the world. It does a sampling design for you. It can do pixel, but also polygon-based and pixel-based and point-based validation. And then it provides you with a confusion matrix and different metrics on accuracy. Also, another tool is very closely mimicking the land use area frame sample Lucas through crowdsourcing, PhotoQuest Go. It can also be used to collect ground reference data for Copernicus potentially in the future. And now I would like to already come to the Crowd to Train project, where we, as I said, use PicturePile. We've been running this campaign for, actually, this is just from July 2020 to July 2021, where we have an increase in the number of people contributing. Is a constant increase because this is the link to the Earth Challenge network and the Earth Challenge app. It's integrated in that, and that's why we do have kind of continuous flow of data, and always new volunteers are continuously being recruited. This is an end-to-end use case, and the company Synergize and Progman are also part of it. This is a contract change notification project as part of the Eurodata Cube run by Synergize and Progman. And we have demonstrated already this end-to-end use case where you can label through this PicturePile platform, but then at the same time also produce in the end a crop type map. At the moment, this is just in the demo phase, but we are working on also getting this to some degree operational, that it can be used by anybody for getting crop labels. And we have implemented also some quality control functions. So the crowd, is being checked, but there has to be also a minimum of 5 people agreeing on the crop type. We are also checking this with a land parcel information system in France and in Latvia. And we are also kind of trying then to use existing segmentation algorithms. So initially you then segment any landscape, and then you come up with a crop type classification where these segments get then labeled and classified. Initially, the training data is provided, and then the classification will then produce the crop type maps. Street level photography, any street level photography, Google Street View, but also Mapillary can be used, and other street level based photography. So down you see here the segments. We then point in particularly Google Street View. This is very easy to the centroid of the segment. We can also point to the segment of an existing centroid of an existing parcel if we have the parcel information like in Europe available. So for that we get actually really good results. And then you see the crop. We do this during the growing season, so we stratify for that. And then you can basically slide into the specific appropriate class using this picture pile. And we have this dynamic wheel where we can adjust also for any region in the world, where this wheel then uses the most important and most relevant types of crops. This is just an example for France. These are the points we have already collected. When we there produce the confusion matrix we get, and when we compare with the land parcel information in France, for example, we get really a high accuracy of nearly 95% overall accuracy, and that is really encouraging that this actually can be used specifically in Europe and the US, where we have larger fields. But when we really use the existing fields, when we use the segments, and when we let the segments being produced by an algorithm, we are having more problems actually. But we've also checked, some areas where we compared with the land parcel, and we think we have even identified some wrong declarations in the past, because there was some subsidies for rapeseed, but clearly these fields are not rapeseed. You can see that, and that is exactly at the time when Street View was going over this area. So we have the precise date, and this is clear that this is in a field which might have been wrongly declared. And with that I stop. If you have any questions, let me know. And I don't know if there is much time, so just continue, Matteo. If sorry, you Matteo, Patrick, if you want to kind of move on.
Thanks, Stefan. Thanks a lot. Yes, crowd to train. There's a few really nice elements being combined there: street level photography, crowdsourced annotations, automatically delineated segments, and quality check through multiple votes and everything. There's really a good elements in there that I like a lot. Let's move to the next presenter though, and this is our colleagues from FAO. Alfonso Sanchez-Paus presenting the initiatives from FAO, Collect Earth, and the Africa Open Deal dataset. Alfonso, please. So far, I don't hear you, and the presentation looks good. Thanks.
Thank you. All right, so good morning to everyone. My name is Alfonso Sanchez-Paus. I am working as a land monitoring specialist in FAO, and I'm the product manager of Collect Earth, which is a plot labeling tool that uses some methodology that we call augmented visual interpretation. Collect Earth is part of what we call the Open Forest Initiative, which is just a set of free and open source software that has been developed within different departments on FAO for both data collection on in situ data collection or data collection using satellite imagery, as well as remote sensing and GIS tools such as CPAL and the Earth Map. In particular, Collect Earth has been developed since 2013, so that was our first version. And we have now over 30,000 downloads. It's downloads because Collect Earth is actually a desktop application, is not a cloud application. Our mission when we started developing Collect Earth was always to improve the activity data reporting capacity in developing countries. We were having real problems doing their land use and land use change assessments for their greenhouse gas inventories and their forest reference emission levels. So we developed this sampling approach, which using this augmented visual interpretation methodology to make it easier for them rather than use change maps. The goal is to make the process really simple for the geospatial data collection, so anyone can do it without having to be an expert on geospatial or remote sensing analysis. We need to be sustainable, so we need to use free and open data. Anything we can find for free, we integrate in Collect Earth. We don't really do much in Collect Earth. We just integrate things that are already available online. And the main goal at the end is that we can achieve that the countries report these biannually update reports every 2 years with data that they can collect easily. So we call this augmented visual interpretation, the way that Collect Earth works. That's because Collect Earth is just a very thin data collection tool. This is installed in the user's computer that is tightly integrated specifically with Google Earth Pro. Because Google Earth Pro gives us this really great access to very high resolution imagery, which for our experience is of course the most useful imagery when one has to do this kind of land use, land cover analysis. Sentinel-2, Planet, Landsat, they help, but it's not the same as very high resolution imagery, right? But we need to combine this very high resolution imagery with the time machine that is given or kind of presented to us by Google Earth Engine that allows us to give every plot whether we assess in Collect Earth, we can have a historical perspective. Very simply put, in Collect Earth, we are usually using a sampling approach with systematic grids or random grids, but you could even use your own. You have vectors that you need to, or polygons that you need to assess. You could just also upload those polygons, and you don't need to actually use like a systematic random approach. But anyway, once your user has a polygon loaded or a plot loaded in Google Earth through Collect Earth, you click on the plot, and there is a form that appears, and the user can fill the data with a big focus on land use change. This is our main thought. We need to collect the land use, but also land use change or land cover change. So again, in Collect Earth, once the plot is clicked in Google Earth, we are able to also integrate many other sources of imagery because, as we say, we need to get everything that is available online. So we have integrations with, of course, the Google Earth Engine. We have Bing Maps, Yandex, Baidu. You can also integrate WMS servers like the ones that from the Inspire projects of the European Union. We also have the integration to Planet data, to Maxar. That's not free. You have to pay a license for that, for the Maxar Secure Watch imagery, but we can also integrate with that for those that have that. Of course, this is just a demonstration of what we speak of why we use Google Earth is because we have the access to this historical imagery that is still not available anywhere else that in Google Earth Pro, not in Google Maps or Google Earth Web or so far this is the only place that has the archive of very high resolution imagery. Again, not everything is in the very high resolution imagery of Google Earth. We sometimes need to also, well, most times we also need to access the Sentinel-2, the Landsat imagery. And for that, there is also an integration in Google in Collect Earth that allows us to look at the NDVI trends and to look at the specific images from Sentinel-2. We can look at mosaic images, or we can go specific day-by-day imagery, loading images to know when deforestation event, like in this case, which is a deforestation event in Belize, sugarcane conversion. Okay. Again, we also have this NICFI purchase planet imagery, but that's only available in tropical, more or less tropical countries, not everywhere around the world. But this gives us monthly mosaics that go up to now September. That's this year. As I said, we do have a sampling approach. You can use different types of grids. You can have different stratifications, different intensities. It's up to the user. The user decides how do they want to collect the data, and what type of intensities, or if they just want to have polygons. As I say, you also have flexibility on type of layouts that you can use. Squares, circles, hexagons, or just even whatever type of polygon you have as a shapefile, you can also use, or KML. And the workflow is let's say the little bit more complicated part, because this requires that there is a type of super user that sets up a data collection campaign. And this super user is going to create this response design with something that we call Open First Collect, which is like the kind of like the mother or the father of collectors. And it has a survey designer. So you can create any kind of survey that you like, any kind of response design with very complex ones if you want to. Like we have like hundreds of ones, some of them from WRI that have like hundreds of questions. So it's up to the user to make it complicated or not. I would say don't complicate it too much, because then it just becomes a real hassle to analyze the data. Then you create the sampling design. The super user will also create the sampling design or design where the data is going to be collected. And finally, you have a data collection campaign where you have like multiple users. Well, usually we call this a mapathon. When we have what we have not in our experience, the most useful case is when a user, when you have multiple users collecting data together in a single room, or in a I don't know, in a classroom, or any kind of way to homogenize the concept and the interpretation of the imagery. This is a big difference. When you do that, instead of having people spread around, that the interpretation becomes less homogeneous. And finally, this super user at the end, once the data is collected, will gather all the data from all the participants and be able to aggregate it into a single database. And we have something called Saiku, which is a business intelligence analysis tool. Okay, we have done this in many, many places. We have done collectors assessments in probably more than 40, 50 countries. It's a lot of countries now. Basically, every country that you work with in Africa or South America, or mostly Asia as well, will have already a database of collectors plots. Okay, so this is something to keep in mind. From our group, we have also started, we started in 2018 a campaign called Africa Open Deal, where it's called Deal for Data for Environment, Agriculture and Land. And it has the goal to increase the country capacity for land monitoring in those countries that we haven't already collected data, and to also act as a way to improve the reporting for the UNFCCC and the UNCCD and so on. But basically, this is a campaign where 330,000 plots have been collected in all over Africa. We have had over 200 photo interpreters, and we have organized many trainings and what we call the mapathons to collect the data in this kind of together environment. And we have a big also focus to improve the Great Green Wall understanding of the baseline of the Great Green Wall and the Great Green Wall dynamics. The data collected on the Africa Open Deal, we have a lot of data. I think we have over 100 variables. But the most important for you guys on artificial intelligence, I guess, is that we have data on land cover. And I don't use it very well, but this is the plot. This is a half a hectare plot. For each one of these half a hectare plot, we have collected the percentage of the land cover, and we have these different elements of land cover. And then we have also collected the land use of the plots and not only to collect the land use at 2019 or 2018, but also to collect the changes, because we use this Google Earth Engine, time series, or historical data to also understand the changes. So we have data from both 2018, but we can extend that all the way to 2000. Yes, it's not quite ready yet. We're still running to clean all the data and to have it ready. And the technical report and the first analysis will come on February 2022. But once that is done, these 330 plots, 330,000 plots will be useful for everyone and open for everyone. And this is really our goal, that this is called Africa Open Deal. So it will have to be open. So thank you very much. And if you have any questions, just send them to me by mail. And I think I'm on time, more or less. Yes. Is there any question? So I think I saw a question, but I cannot go back to the chat. Now I'm a bit lost with WebEx. How do you do this?
Yes, thank you very much, Alfonso. One question was around the openness of the data set. So you mentioned that in your last point that some of this data in Africa will be open, but is there any data currently, lots has been collected. Is there any of the data being open?
Sadly, I mean, when we collect data, it's not FAO collecting data, it's the countries collecting data. So we don't own the data. And in fact, in Collect Earth, we don't even have a database. Like all the data is stored in the computers of the
Exactly.
users. So they are completely owners of this data.
Yeah.
And most of them don't want to share. And this is a problem. And I still don't understand why it's such a problem to share, because we are speaking about data collected through Google Earth. So anyone could actually do this if they wanted to. But so this is the idea of with Africa Open Deal, that we are going to make it open.
Okay, thank you very much. Clearly some scope for improvement there.
Yeah.
and understanding it as well. Yeah. Thanks very much. Let's go to the next presentation. The next presentation will be given by Raphaël D'Entremont from the Joint Research Center, and it will be about rateseed mapping using street level photography and Lucas Copernicus module. Over to you, Raphael.
Yeah, good morning, everyone. Can you hear me?
Yes, we can. Thank you.
Okay. Can you see my presentation? Not in
Yes.
full screen mode yet.
Not yet full screen, but
It's coming. It's okay?
Yep. Yes. Thank you.
You have okay, good. So good morning, everyone. Thank you for giving me the opportunity to present some of our work here. So I'm from the Joint Research Center of the European Commission, basically providing scientific evidence to policy and also doing scientific research. And most of the thing I will present today have been done mainly in the Digital Rural Landscape Lab.
Is the other screen?
Sorry?
You might want to switch the presenter view.
So you have the other screen. Okay. It's me. So that's why I was asking. Swap presenter. Thank you. Is it good now?
Yes, it's fine now.
Thank you.
Thank you.
I'm going on. So here the work I will show, it's from all the group, and basically I will try to do a medley of ongoing research. So you see that the title is not the one on the program, because I've a bit presenting also other research ongoing. Yeah, that's a bit. You remember in the old time when we were speaking about big data, basically there was this 5V that were used, and I think, and it was already highlighted by the presenter at the beginning, that we are really at the golden age, as was Patrick saying. Now we have the velocity, the volume, and variety, especially for agriculture in EU. We have more than 70 millions of agricultural parcels that are observed more than 300 times per year. So we have a huge amount of data, but also a variety of data that we are probably not yet fully harvesting, such as weather data, market information, and so on. But there are still 2V missing in these slides, which are the veracity and value. So veracity, it's like mainly ground true and high quality information, and value is information useful for user. So it could be for farmer, citizen, rural economy, industry, or stakeholders, basically. And in fact, this is a bit the core of our activities there. We are working on both this topic, basically in support for policy. And today I will present you some examples and some application, mostly related to administration data, survey, and crowdsourcing. So we will not speak too much about farmers' data. A first example that I will show you, it's about the Lucas data. It was already basically mentioned by Stefan previously, but Lucas is the land use and land cover area frame sample. So it's the in situ effort of the European Union, basically. And you were saying, Stefan, that not a lot of money is invested in situ data for EO. I fully agree with you. But Lucas, even if it was not designed for EO, but for statistic, it was run in the last 15 years for a total budget of about 45 million euros. So it's still a lot of money. And in fact, here in this study, what we've done is that we have harmonized the data that were basically collected with different protocol every year. So the result of this work is a 1.3 million records with an harmonized legend and tables, basically. As you can see on the right, you see the date of the survey, and you have a very high number of information, up to more than 100 variables. Also, it's not written here, but the data are available also on Google Earth Engine as a data set. I will show you some follow-up of this study, basically. And also keep in mind, you see here down that in addition to this 1.3 million, there were 5.4 million of photos collected during these 15 years, basically, mainly landscape photos looking in the 4 cardinal direction. I will go back on this topic afterwards. What is also interesting to mention here is that in 2018, there was a pilot called Lucas Copernicus, which is a specific subset of the Lucas sample. So as I said previously, Lucas is designed for statistics and not for Earth observation. And here was the first attempt, basically, of this campaign to look for data useful for Earth observation. And in fact, there were 60,000 pure polygons collected instead of points that are subtraction of the pixels. And it was published as an open dataset as well that you may be interested in using. And just to show you 2 very recent applications of the dataset that we've done in the group. One was using these polygons basically to assess the phenology from Sentinel-1 and Sentinel-2 over Europe. And basically it was validated with ground truth information that you can see on the left. It's a study that was led by Michele Meroni. And the one on the right is the first 10-meter Eurocrop type map, basically, based on Sentinel-1 data and the Lucas Copernicus. We were able to provide a 10-meter resolution parcel map. So just to highlight the importance of such type of data. And what is very interesting also to know for you probably is that there will be next year in 2022 a Lucas Copernicus module with 150,000 sampling basically, so much bigger than the previous one, and with a simplified protocol basically. Okay, so that was about the Lucas Copernicus module. Now I will show you some research that have been done in the lab by Laura Martinez Sanchez, basically where she's using the landscape photos. Here, for example, you see basically a semantic segmentation that was done based on Deep Lab version 3. It's a model basically to segment the image in different classes. And basically, in this study, we have shown that you could use such type of information from the pictures to basically connect with land cover. Another study that is ongoing also, that is ongoing with Laura and Daniele Borio, is basically using these pictures to derive the openness of the landscape. So you see, for example, here down on the image that you can basically get the horizon line directly thanks to computer vision, And also you can get for each of the different legends, you get the class below the horizon line. By combining this plus measurement that have been done on orthophoto for many points, basically, we were able to derive metrics in order to estimate the pseudo distance from the image directly without using any remote sensing. So this is really exciting result, basically, because it's really merging the 2D from the orthophoto into the 3D from the basically street level imagery. So we are looking forward to process this. Another interesting thing to mention is this data set that we've been producing. So we had a little contract where we basically have done a sample of 3,000 images of Lucas, and that were manually edited and segmented and annotated for 29 classes, which are relevant for landscape and crop field in the EU. So at the end, we have more than 10,000 objects that were delineated, and we hope to be able to share this data set very soon in order to be used for the scientific community. This is also very interesting to mention. So when we did all this work with Eurostat, with the Lucas data, we discovered by chance that there was another type of photo collected every time in the last 15 years, but these photos are not public. So this is the so-called cover pictures or close-up photos. And there are 850,000 of these photos, as you can see here, for the different years. And in fact, thanks to our push on the data, basically anonymization is ongoing, and the data should be public also very soon. At the same time, we have started and initiated research, basically, to study if we can use this data set to classify the different crops. Here you see an example with 15,000 pictures for which we have used MobileNet V2 and EfficientNet. And also with the same data set, basically, the full data set, we are collaborating with PlantNet. Maybe you heard about it. So PlantNet is an app that you can install on your phone to basically classify any type of vegetation. And there is no European crops branch in the PlantNet that being developed that was basically fed by this Lucas cover image. This is something else, not related to Lucas, but more to the parcel extraction. I'm just saying it very briefly, but we are building a data set basically in order to have parcel delineation data that could be used for benchmarking in EU. Here, basically, we have used 7 different countries in or region in the EU for which you have open access parcel delineation. And we've done a stratified sample and extract different type of data sets, Sentinel-2, Sentinel-2 time series cloud-free, and orthophoto resample at 1 meter. And this would be used basically for benchmarking field delineation methods in the scientific community. I think I'm running out of time because I was planning to give a presentation of 15 minutes, and I understand it's 10 minutes. So I will drop this, but you can check the reference. Maybe I will just mention this because it was mentioned by Stefan at the beginning, and I think it's a key interest for many of you. Is the Copernicus for GeoGlam services. So this is a tender that was tendered by the GRC, and it's led by Michele Meroni and Felix Rembold. So this is their slide basically, and they operate this contract with CLS and TerraSphere, and it's basically the contribution in support to GeoGlam. So I will just show you the type of data that's being collected. We have 3 sites, basically Tanzania, Kenya, and Uganda. You can see it's a subset of the country, but for all of this country, there were data collected on the field with a proper sampling, also street view imagery. And yeah, you see here, for example, on top that the parcel, the grid basically was 500 by 500 meter was pre-delineated, and the surveyor were going on the field basically to check if it was correct. Well, so just for you to know, this data set will also be published, obviously, and yeah, I'm not directly myself working on the data, but I will be pleased to connect to the people working on the data if you have any interest there. And this is a good link to my conclusion, basically, that we demonstrate that repurposing historical statistical data thanks to artificial intelligence could bring a lot of added value, basically. We are also combining computer vision with street view imagery to provide new type of information stream. Well, the key goal there is to support policy for us and to bring value and veracity, but it's a long way, obviously. And as you can see, and also we are supporting in situ data collection as much as we can, even if it's true what Stefan was saying at the beginning is that it's not always sexy to fund this kind of of data collection for the public money. And well, the thing is we're trying to bring this kind of technology in the key policies in the EU that are related to urban landscape, basically. And the last point is that we have a scientific session in the LPIS that will be organized. So Patrick mentioned it at the beginning, that there will be probably many of you present at the LPS next year. And in fact, some of you were already presenting there. We did this session basically at the last one. It was the first time. It was a real success. And yeah, I hope to see you there. I think there are a lot. I mean, the maturity is coming a bit in the field, and we still a lot of work to do. So I'm looking forward with. And sorry if I brought a bit over time. Over to you.
Thanks, Raphael. A fantastic overview of relevant, really interesting research going on at JRC. Really great. I love the examples where you use new machine learning and AI to simply improve the reference data that we can derive from open data sources such as street level photography. That's really cool. So thanks a lot. And okay, let's move to the next presentation. And remember, you can continue asking Raphael some questions in the chat here while we continue. So this is now leading to the next set of presentations, and they deal with the reference and training data collection that was done for the ESA World Serial project. And the first presentation will be given by Hendrik Bogard. Hendrik, the floor is yours.
Yes, thanks. Thanks for inviting me for this session. My name is Hendrik Bogard, and I would like to, oh, sorry, I have to go back to the first slide. You can see my screen? The presentation? Yeah, thanks.
Yes, we see.
Yes.
So, Hendrik Bogard from Wageningen University and Research. I would like to present on our work that we did for World Serial on collecting and harmonizing reference data for in support of crop mapping. So first, yeah, it's obvious why do we need up-to-date crop length and crop type maps? They are essential for all kinds of applications on, let's say, monitoring of crop growth, crop yield forecasting, or studying yield gaps, etc. So that's clear. And in World Serial, we are prototyping and implementing an open system to produce a global annual cropland extent at 10 meters, taking into account also seasonality to make that available just after the season, distinguish between rain-fed and actively irrigated cropland, so the water management, and also going to the crop type level, so global crop type maps of maize and wheat, also at the 10-meter resolution just after the season ends. Yeah, you can find more about World Serial through that URL. I would like to focus on the collection and the harmonization of that reference data. But to do this kind of work, you need sufficient high quality, and we promote open reference data for training and validation on land cover, crop type, and irrigation. So let's kind of specify the reference data that we're talking about. We are distinguishing different types of data, 4 types: field observation surveys, so observations really in the field. What already was presented by Stefan on crowdsource and expert campaigns on classified maps, so these wiki-like things. You can also use classified maps, like we also have collected a cropland data layer from the USA for our work here, but then we take a sample and not take the whole data set. And also the parcel registrations, if they're open. For instance, we are using data from France and Austria and other countries in Western Europe. And also there we take a sample of the original data set to limit the amount of data and also to avoid bias. So these 4 types we distinguish. And then, of course, the data needs a kind of geolocation, either a point or a polygon. We're interested in data from 2017 onwards, so the Sentinel era. And of course, the data should have an timing, so at least a year or year season, preferably a real date. And then an observation of land cover, crop type, and or irrigation. And also to really understand the data, we need also more information about the data set so that we can interpret the data and also know more about what we can do with the data, how we can share the data or not. So that the background is also, of course, important. You also see this little figure here that will be presented by the next speaker, where we show a kind of upload of the data sets in the World Serial. So there is no real current solution of sufficient high quality open reference data. So we started a kind of journey. So that is 4 elements of the journey. So data discovery. And once you have found the data, you have to harmonize the data, put it in the right format, translate it into our legends of crop type code, for instance. But we're also looking at the data, the fitness for the use. Can we really use that kind of data? And finally, we would like to publish the data. But this journey is, and we discovered that World Serial is now halfway. So we are 1 year we did and 1 year to go. So this is a challenging task. So the accessibility of the data scattered over many different sources. Yes, of course, the lack of standardization. There is no, all these sources have different formats, different crop codes. And you also need to know more about the background to get most out of that data and also avoid mistakes, misuse of the data. And finally, you also have to take care about all the ethical, legal, consent-related restrictions before to know if you can share the data or not, or what you can do with the data. So going to the first data discovery during our data discovery, we engage with the community, with many different players. So for instance, NASA Harvest Initiative, the CGR, also publishing through Guardian, the USDA, just mentioned Copernicus for GeoGLEM, LACO Wiki, Radiant Earth, so many different players that we engage with. We had meetings, questionnaires, we collected data from all these sources. And you see from left to right that on the left you have the more public ones, and on the right you have the private ones. So we also have data that has been shared with us that we cannot open, but we can use it for the training. So these are the different sources and organizations we met with, engaged with. FAO also to be mentioned, but yeah, there are many here. Next. Hope I can go to the next one. Yeah. Then after you have collected the data, we have developed a kind of protocol to harmonize the data. That means that we prepare the data in the desired format, shapefile with correct file name, added additional attributes to hold the crop type and the land cover type, etc. Also a protocol for a proper assessment of the validity date that we need. For instance, if you only have a year and a season, then we use the crop calendar to come to a real date that is in the middle of the crop calendar. We prefer, of course, the real date, but if we only have a year, then we use the crop calendar to assess a validity date. Then we map to the World Serial legends on land cover, crop type, and irrigation. And if you want to use the World Serial system that will be soon launched, then you can upload your data. If you want to use it only for private use, then we define only very limited metadata. So that is about a title and that you can recognize the data. So, but before you can use the data, you need to do this data harmonization. So prepare the data in the right format, mapping to the legends, and define some limited metadata. And we have some supporting documents that are useful in that harmonization. It's quite lightweighted procedure. This is an example of Remagaldo. This is a data set published in Scientific Data in Asia, Central Asia. We took this as an example. So we downloaded the data. Next, we copied and saved the data under a new name, shapefile. We added attributes. So first, we have a kind of standardization of the name. We added attributes on crop type, land cover, irrigation, the timing, and a unique ID of each record. And then we just simply map the crop codes towards our legend. We assess the validity time and we add these unique IDs. And then we have kind of harmonized that data. We add a minimum set of metadata, title, unique name, the data type, the 4 types I just mentioned, and a first assessment of the accuracy of the data set by the owner that's uploading the data. But in World Serial, we are promoting opening the data. So, and to open and share the data with the public, you need to do some more effort. That means you need to organize more metadata on the observation method, what type of method it was. Is it a real point data, or and was that the observation on that specific point, or was it representing a kind of radius of a few kilometers? That could happen. So the observation method, was the data validated after acquisition? On the background, maybe there was some information that all the observations related to irrigated areas. That in Remagaldo, that's the case. So then you don't have the real observation of irrigation per polygon, but you know it's all irrigated, so you have additional information there. But also metadata on the owner, affiliation, the data policy, what kind of citation would be required if you open the data. And we use the data to make a better assessment of the accuracy, both in space, in time, and in thematic accuracy for those 4 different types. And that helps us to select the data for training and validation. For instance, the higher accuracy could be used more for validation, and the lower accuracy maybe more for training. And it could also be used just this weight. We have developed rules, and in the end, we have one figure for accuracy that can be used in the training as a weight. So this is done together with the World Serial moderator to then describe the data and then publish the data. This is an example where we have the template in Excel, and in the green column, we just fill the data, the additional metadata. This is an example of a rule where we say, well, the Remagaldo data, the GPS info is not there, but there are no issues in the data and then we give it here a score of 100, and the other scores, it's real date, the validation was applied, so we have a very high accuracy score in this case. So we use those rules, and then what we have now in World Serial is around 88 data sets. You see how they are spread over the world. We have around 170,000 observations. Most of them are public, a few of them are private, and you see that we still have quite some gaps, specifically in Asia. Also some gaps on spring wheat, that's little data, and on the water management itself. So this is the current status. So next steps in World Serial is that we continue to engage with the community and enrich this World Serial reference data repository. We're also talking, for instance, with private sector to see if we can get data through collaboration there. And we're also thinking about what will happen after World Serial. So sustain this initiative, and we're talking with GeoGlam with the in situ working group to host it there. I already mentioned that we promote open data, and why should you open and share your data? Well, there are obvious things like if you are an owner, a researcher, you become more visible. You will have the attribution if you publish. It's also kind of social responsibility if you use public money, and funds like Gates also asking to open your data if you collect it through their funds. Contribute to open science, increase your impact of individual research data. And then within World Serial, we have some additional advantages. This reference data repository will be soon released and activated for specific users this December. And by the end of the project, we will open it to the public. But if you would share the next months, next half year, you will have the advantage to already look at our reference data repository and make use of it. And we also think about writing a high-level paper on the work we've done, and then if you share the data, you could become co-author. At least we could discuss that. And I think the last one, and that's a nice bridge to the next presentation, is that in World Serial we're offering a very easy guided procedure to upload and publish your data set, and that is something that Santosh will present after my presentation. I think with this, I'm at the end of my presentation. Thanks for your attention.
Thank you very much, Hendrik. That was very comprehensive and it gave us a very good overview of the work going on in World Serial. This is a joint effort between Wageningen and YASA, particularly on the reference module. The project is led by Vito, as said, and we are working closely together here to really open up more data and also to provide this specific reference tool, which Hendrik has upload tool, which Santosh is going to now present. So Santosh Karanam is going to show us how this reference tool works real time. He's going to give us a presentation on that. And as said, there are many incentives now for some of you, or you might also know somebody maybe in Asia or in Australia, where we currently don't have any reference data. Please be so kind and prompt those people to potentially also share their data. And there are a lot of incentives beside as we have heard, the social and the environmental responsibility. I think we all have to open up more data. So over to you, Santosh, to give us a brief overview, and then after that, I think we are then going into the break. Thanks, Santosh. The floor is yours. We can't hear you. Are you muted?
Yeah, now can you hear me?
Yes, we can.
Sure.
Now we can see the presentation. Perfect.
Okay, yeah. So this demo would be like complementary to the previous presentation. I have just 2 slides and then we'll move on to the demo. So basically, I have here an overview of the reference data module. So a reference data module consists of consortium store and the community store. In the consortium store, we have the datasets which are harvested, harmonized, and curated and maintained by the consortium, which is the project partners, and will be used for product generation. And the second store is the community store, where users can contribute their datasets. In both the stores, we have 2 access levels. One is the public and the private. In the consortium store, if the dataset is public, it will be available for all the users. Private datasets in the consortium store are shared to the project with the clause that it cannot be shared public. So those will be maintained as private. In the community store, whenever the user uploads the dataset, by default, it will be the private dataset. And user can follow certain protocols and guidelines to and work with the moderator to make it public. Once it is public, it will be accessible to all the users and also to the consortium. While making public, we have a few license suggestions, as you can see in the slide. A user can use one of these Creative Commons license or suggest his own license and then make the dataset public. The second slide is more about information about how you can access the website. Here we have a short video tutorial in the first, and then there is a website URL and the login access. The login would be active till 23rd October. That's like 1 week from now. And post that, users can mail to the moderator at World Serial mail ID to get individual logins. And we also have different links to the harmonization documents. With this, I'll move on to the demo part. Hope you're able to see the web interface. Yeah. So this is the reference data module web interface, which has a short description about the project and the introduction to the module. From here, you can actually directly go and contribute the dataset or explore the consortium datasets. First, let's go and see how you can contribute to the community store. So the first step before you actually go into contributing the dataset is to answer a few questions where to make the dataset usable in the further processing chain. So we basically require three information: whether the dataset has geometry, or whether the observation time of the dataset has onwards from 2017 observation time, and whether the observation time is the actual time or derived from season of the year or the actual year itself. If at all any of these fails, then the dataset cannot be used in the further processing chain, and we prevent it from uploading. So user can answer these questions and then go to the next step. In the next step, we have this 4 steps where we help user to do the preparation of the data. So we actually accept data only in the EPSG 4326 format, and we actually have a mandatory fields which needs to be present in the dataset, and the data in the dataset has to be mapped to these mandatory fields, and also certain optional fields can also be present. During upload, we actually do the validation checks for all these mandatory attributes and the values in the attributes. And also we have a short guide how you can derive the validity time. All these documents are downloadable through the links provided here. You can just click on them and then download. Once you have all the information, you can map and prepare the dataset. Once you have the dataset ready with you, this is a small web interface where you can give a title, a short title. I'll just show a small upload demo here. And then you can select the type of observation method, whether it's a field observation survey, how the data set was collected, whether there was some classification validated by the crowd or expert. You can choose any one of these. And then based on the quality of the data from the user's perspective, you can give the quality score for the crop type information in the dataset, and the land cover information in the dataset, and also irrigation. If at all any information is not present, you can just leave it as 0. And then you can select the dataset here. It's a zip file containing shape files. So I have just prepared a small zip file here. And then once you have selected the zip file, then you can click on submit. Once the dataset is uploaded, the dataset goes through the initial validation checks for checking the mandatory fields and also the values in the each of the attributes. Once it is validated, it will be stored in the database, and it will be available only for the user as a private dataset. So this is the view where after successfully uploading the dataset, you can see. And also you can browse through all the dataset which the user has uploaded in the user collections page. Like I told, if at all there is a validation failure, you can you can go and check what are the errors here by clicking on the show errors button. So here it says that the attributes which were supposed to be present are missing, and also some of the attributes have invalid values. And also for optional attributes, if at all it is present, then the values also are checked whether they are valid or not. So all these checks are made. So once you have fixed all the errors, you can again go and upload the dataset in the same page. Once it is uploaded, again, it will be available in the module for private use. And also this dataset can be used in the further processing chain to generate the products along with the other datasets from the consortium. So once we have the dataset uploaded, the user can choose to make the dataset public. So to make the dataset public, we have certain guidelines, like already those guidelines were explained by Hendrik. So I will just show the UI here. You can just click on this make public button so that you can navigate to the instructions. The first thing is to make sure that the geometry of the dataset is proper by visually interpreting that or by any other tools. We have a guide. We have a guidelines document here. You can click on this and download, and also the confidence scores which user has entered initially while uploading needs to be standardized here. We have a simple calculator here and a guidelines document here on how to do the confidence calculation score. And once this is all ready, then you can download the actual metadata document by clicking on the a link here, which will come pre-filled with the details of the dataset. And once it is ready, you can upload it. Upload the metadata back by after filling that. And once you have all the things ready, then you can submit the data for making it public. And from now on, the review process starts. As you can see here, there are logs printed for different review comments. If the moderator will download the shapefiles and also the metadata document and then check if there are any errors or any problems with the dataset. If it is not, then he will just make it public. So one of the, just to show what all the comments you can see in the review. So here, the user has not entered the license, so the moderator has sent back the dataset for uploading the license type in the metadata. So once all these things are done, then the dataset can be made public. Once it is made public, it will be available in the Explorer for everyone to have a look. And then from here, you can click on any of the dataset and then go to the dataset details page with all the metadata metadata field. So here you get the details of the dataset and the confidence scores and the dataset provider details. For two of the datasets which were earlier mentioned, the Ramalgado dataset, we allow the dataset to be downloaded. So user can actually download this dataset and see how the harmonization is done. So yeah, with this, I conclude my presentation. I hope I'm not overshooting the time.
Fantastic, Santosh. Thank you. No, that was perfect. And it's great to see all the things that you have thought of for the data ingestion and the quality control. I think that's really excellent. Surprising that there's still so much use of the shapefile format, but we don't have to discuss data formats, so that's fine. Okay. I think in the agenda, the next thing would be that we have a 5-minute break. And I think that makes sense, Stefan, that we do the break now. And then start with the second block at 10:45. Let's start punctual.
Yes.
And then we have another 5 presentations. And then we would, we have some time to discuss those questions that were maybe unanswered in the chat. And we'll do the live polling then probably during the discussion, okay?
Hello, everybody. I guess we should get back. Don't know, Patrick, if you wanted to say some more introductory words to the next session. If not, just chip in. You want to say something?
Well, I mean, the first block of presentations that we've seen that's really mostly on new methods and new approaches, new tools for training and reference data. And now we're moving a little bit more to the larger, broader community initiatives here. And the first one is a little Pathfinder project that has that's just being concluded, the ARIO, so looking at AI-ready training data sets, and the pathway to making training and reference data fair data compliant. That's the first talk in this new block of sessions, and we'll hand over to Alistair here from iCheck to present this. I'll
Thank
stop
you.
sharing.
Okay. So that you can see that, I hope.
Yes, we can.
Good. Okay. Okay, so this is AI-ready data, Earth observation data sets, and as Patrick pointed out before, basically we're setting out to solve the problem that training data sets are crucial, but there's a bottleneck of availability, the lack of interoperability between the data sets, and lack of best practices to work against. So we set against that, and we built up an area specification for AI-ready data sets. After going through a community consultation process, we basically settled on using the stack formats to make sure that everything was cloud ready, but OGC standards, everything that could then interoperate with existing formats like the CDF Geo package. The aim is that everything works with existing machine learning toolkits. So we take predictive features from the Earth observation data, reference data from other grand campaigns, and make it possible to train against those models basically on the ImageNet data sets that you already get with the likes of PyTorch, etc. All of these then we developed a set of pilot training data sets to demonstrate this, and a library for making all of these work. So the pilot, we worked on 4 pilot data sets, a biomass retrieval one from forest plots, Arctic sea ice, which uses Sentinel data, Arctic sea ice, which uses Sentinel-1 data, and microwave data. So we have a combined set of 2 data sets. The Common Agricultural Policy one for boundary classification, and an urban temporal development one with images on lots of locations for urban use. So between these, we have tasks. We have a number of different AI type tasks. We have regression, correlation, segmentation, identification. And what we built basically is a data model based on existing data sets. So presuming or work against a stack type data sets that pre-exist. We created creation methods in the library for building a model based on these. We can describe feature recipes on how to create that. So within the specification, the idea is that you can document how the steps to create the data set are produced in GL-like or CML, and document the benchmark fixed sets that are aligned to make it possible to create the data set and recreate the data set later. For example, we will work against an initial data set, an initial benchmarks data sets that might be several gigabytes in size, that a user can download a fixed version to their own home system and try out in machine learning models. But once they've got a model working on the given data set, they can recreate it later to update the data set based on dynamic sub-collections that are online. And this is kind of how it works. Based on how it works, we have the code is basically written for the biomass data set demonstrated here. We have it libraries written in the pilot data sets in the Python Jupyter libraries, which we can. So when you've got the data sets in the Jupyter libraries, you can explore these system setups, explore the variables that are available that are made available from the reference data for you to work on, and do training on the Earth observation data. In the specification, we came up with the idea. We basically enhanced the stack specification slightly with the concept of profiles. What we wanted to do is for our users to be able to explore the data sets, to work with it, and know what data will be always available in an area training data set specification. And for that, the profiles basically will define what data and what metadata will be present in a given training data set. So all elements in an area data TDS will have a set that are defined as core elements, basically identification, versioning, etc. If they, depending on what they provide, they may also match a number of other profiles. And if they do, then extra data and metadata will be available. So for example, if your data has georeferenced Earth observation images in it, most of the examples we just listed all have, then you can guarantee that there will be things like the CRS and georeferencing within the data set, and your code can work and libraries can be built against that. So you can basically do inference on the data set to see what is capable with a given data set. All of the data sets we've listed in the pilots are all have imagery, but the concepts can stretch, and new profiles can be added later for point clouds such as LiDAR, for aperture composition, etc. All of the metadata that we list off is then defined in the standard. It's almost all built on existing standards such as Stack and OGC standards, and we basically list off what will be present in each data set. And for this, we added a set of best practice guidelines. We wanted to basically explain two communities to each other: the Earth observation community and the machine learning community. So for the Earth observation community, we basically describe what labeling needs to be done, how we can characterize quality, how versioning can best be done to work with both sets. So for Earth observation providers, we want EO data providers. We wanted them to explain to them how to describe their data that is best usable for machine learning users, and the libraries and the specifications enable it possible to automatically generate a data sheet for your TDS that will describe all of these details to users. For the reference data that comes from from ground truth or Earth EO data providers, we, for example, go into in the best practices describing the difference between how we represent geospatial temporal differences. So, for example, imagery is typically instantaneous, whereas a lot of our data sets have year averages. We need to capture that so that the users know about this. We provide example, training, validation, test splitting for the machine learning people, and we need to describe how that is best done, how to describe any class imbalances that are present in the data, make sure that the providers are aware of that, and then make sure that the principles of FAIR are done, implemented, so the data is findable, accessible, interoperable, etc. The data sheets help explain how the data was collected, what was the intent of the original data, and that often makes it possible to capture in the metadata subtle details about how and why the data was collected that somebody who just downloads it randomly off the internet might not be aware of. So what does the user need to understand about the data, about data completeness? What about holds? What about missing data? How is that handled? When in a TDS, what ML problems is set out for, is it expected to try and work on, and therefore tuned towards.
Sorry, Alistair, can you come slowly to an end? Sorry, we need to be really strict with timing now in the second slot.
Okay.
That would be great.
So the FAIR metadata basically explains all of the data that we need to provide, DOI, versioning, etc., and how to work with that. We provide a library that works on all of these, that makes it possible to add up your data sets. That provides I/O functionality for the users to have to load in their code of specific data. And this is, for example, how the library works for training, how we can load into a particular model, iterate over the data set fairly straightforwardly to work in that. And the library provides other methods for statistical and validation and visualization to explore the data. And in summary, basically what we provide is a number of features, added quality assurance information into the library for consistency, completeness, provenance, trait, make it possible to extend it, some extensions for that, and embedded feature recipes. Thank you.
Okay, thank you very much, Alistair. I think if there is anything, any questions, maybe we can answer them in the chat box. Don't think we have now time because we're all a bit short. Really, everybody wants to say other things. So let's move to the next presentation. The next presentation is going to be presented by Peng Hu from Wuhan. Training Data Markup Language for Artificial Intelligence, OGC Working Group. Over to you, Peng. Thank you.
Morning and good afternoon. Yeah, this is afternoon in China. So can you see my slide?
Yes, everything is fine. We can also hear you. Thank you.
Okay. Thank you for invitation. I will give a short introduction to the OGC effort on training data markup language. So I think the background everybody knows that for scene level, object level, and pixel level, this training data were organized in different form and in different data content. So we needed the standard. So using a standard for modeling the training data can help us to find the data, to discover the data, following the FAIR principles. So the purpose of this work group is to develop the UML model and encodings for the training data. And we will investigate the existing OGC standard and how they can be extended to use and share geospatial training data. And the first step, we are working on remote sensing. And this is the scope of this defined in the charter for this work group. Actually, the effort was started at the beginning of this year, and it goes through several sessions, public comment, and after the TC vote. And now the preliminary name, the sample markup language, we define, if we use this term, but later, based on the public comment and the TC comment, we change it to the training data markup language. Here is a conceptual model. Actually, when we define the model, we follow in 8 key considerations: the core element, the granularity, the collection level, individual level, the label semantics, because we have different classification scheme for the label semantics, the provenance, quality, the lightweight protocol, so we use JSON, and extensibility, so various machine learning applications can be extended following the high-level model and alignment with the existing OGC effort. So based on the core element defined in that slide, then we define a concrete model. What do we mean the concrete model is that we add the properties in this basic element, like the training data, the data set, the data source, the quality, the labeling. So here shows how we define the basic attributes. When we define these attributes, a basic principle we just mentioned is lightweight. So we just define the basic properties. But people can enrich the high-level model with more properties. So we specify some basic properties in this core element, like the provenance, the label, the tasks, and the quality. For the quality consideration, we define the scene level data quality elements, the object level, the pixel level, because they all have the different focus, like the class imbalance, the image size issue. some of these properties are already defined in the basic attributes of the dataset or the data source. Others can be added as a new quality element in the ISO 15157. So here are some of the quality consideration. We follow the two strategies. The first is add a quality element as attribute, and then we can map the quality element to ISO 19157. Also, we define some quality elements, related element based on user perspective. We add the metrics achieved in the literature, and also some statistics info on the class on the number of instances in each class. And here, based on the data quality element, we define the scene data quality, the object data quality, the pixel level training data quality. And then some data quality element can be extended to the 19156. So for the language encoding, we also define a set of rules. Basically, it's for the JSON encoding, how the UML class can be mapped to the JSON schema, and then next help to define the JSON object for describing the training data. I think all these are the chapter work, and the work group will have the first meeting in this December TC meeting. Here are the various rules. So here shows how we can apply this model to various use cases, like the scene classification. We take a data set on the web, open on the web, and then we show how this UML model can be grounded, instantiated to describe this training data set, like the attributes in the training data set, the metrics, the tasks, the data source, and particularly, I think we already, I can see the previous talk many about the metadata. Here we also show that we think that this is a data markup language, so we are not only about the basic element on the metadata, we also talk about how the data can be encoded. So we show the data pair and its scene label. And then we tested this encoding with machine learning algorithm and show the process. So for the object detection, we have different encoding on the object label and the training data. And here is also a simple workflow. And for the classification, then classification, the training data encoding and the pixel level label, also they have the different organizing form. And we test the JSON encoding with the existing machine learning model. And for change detection, because it already includes the time series images, so we show a simple encoding in the training data and the pixel level label. So here the instance diagram shows from the dataset to the data instance how they can be encoded in this. And finally, they will be transferred into the JSON encoding. This is also a simple scenario using this JSON encoding. We also are proposing how this training AIML can be used in the spatial data infrastructure. Actually, it can serve as a training data interchange language encodings in a service-oriented infrastructure. In this way, we can create the AI-ready spatial data infrastructure. For example, we propose a simple API, the training data API. So the training data from various data sources like files online and the DB, they all can be transformed following the training AIML, UML, and the JSON encoding. Then they can be accessed through a catalog service API, and then people can find the training data store to search for scene level, object level, and the pixel level data. Actually, we also in the last half session we have seen the set of tools, and Wuhan University also developed a training data store and some tools for sharing the data. But the system are in Chinese, in the Chinese version. So here is a simple API. Actually, it follows the OGC API style. So the training data set collection, it's actually a collection. Then based on the collections, the training data set ID, we can search the training data set. For training data, the instance level, we can support the query parameter. So to search the training specific training data. And this is a system. This is a simple system with the English user interface, but actually most of them are in the Chinese interface. So actually, we are preparing the draft standard, and hopefully after the December TC meeting, then we can start the work group. The work group members can working on how to polish the standard draft. So here we just propose the design consideration, a base model for the in this standard, and we propose key considerations, and it can we test it on the use cases like scene, object level, and pixel levels. So, also based on the public comment history, some members in OGCTC also suggest we can enrich the work like the data privacy, the data ethics, and more specific data quality evaluation. And also sometimes because different user community, they have the different classification schemes. So we just provide a mechanism. So like people can introduce different classification schemes into this model. And also some people give comments that we should consider more your tasks. So and also originally we just defined a simple payload for the quality elements, but later people give comments that we already have metadata on like the ISO 19115. We already have the data quality standard like the ISO 19156 or 157. So later some work was devoted on how to align with these existing standards. That's all. Thank you very much.
Thank you very much, Peng, for this very insightful presentation on this OGC activities that you are having with some very concrete examples. With that, maybe not sure if there is a question, or so you can post your questions in the chat. As we know, maybe we try to also move now forward, that we have time also for this last Slido type of questions at the end. So I would then hand over now for the next presentation to Amy Bray or I don't know, maybe it's Karim. I think Karim is presenting actually, to Karim Amar, and it will be an update on the Lacuna Fund labeling campaign. So we're very much looking forward to that. I think Karim is there, right?
Yeah.
Over to you, Karim. Yes.
Thanks, Steven. Thank you. Can you see my screen now?
Yes,
Yes.
we see it well, thanks.
Thank you very much. Okay, so today my name is Karim Amir. I'm the head of AIML at Visual and AI Solution, Vase. Vase is an agri-tech startup, and we are building the next generation of precision agriculture platforms, specific and with focus on the MENA region and African countries. I'm going to present the locational offset correction project. This project was funded by Lacuna, and it was a collaboration between us at Vase and CGIAR, one of the largest agriculture and agronomy research organization, and Zendi, which is a data science platform with 30,000 users that who solves African challenging problems. Okay, so the goal of the project is to correct the location of maize fields center using satellite imagery. So, for example, we have in this image we have the original collected data from the ground in the blue point, but it seems like it's off and it's not in an actual field at all. And the goal is to find and the corrected center is that we labeled is the red point, and we would like to get the displacement vector between the 2 points in order to correct the data set or have the correct field centers. So in order to do this task, we collected the data from multiple sources. First one is Planet Labs images. So we collected 4 images for each field from June and December in 2017, 2018 also. The resolution of Planet Labs was 4-point-meter resolutions, and we only used the RGB channels from the source. We also collected Sentinel-2 images from like a full year on the same field, but Sentinel-2 images has like lower resolution of 10 meters, but on the other side it has like multiple spectral bands, specifically 13. We also used metadata like the yield estimate and the field area per acre, and some data like the year in which the yield estimation was done, and annotation quality. I will discuss what do I mean by the quality later. So in order to use Planet images, we developed an API we call Planet Box Extractor API in order to facilitate the extraction of images given a radius and a specific longitude, latitude, and location. So the API provides 2 key functionalities: stitching tiles together in order to have an image full field, even if it spans on multiple tiles, and crop around the field exactly. And you can find the tool on this link. We developed another tool for annotation based on Google Earth Engine. In this tool, we have like we put the original location marked here in the image as on the red black circle, and the user can or the annotator, expert annotator can change this location and correct it for labeling, which appears here in this image as the red circle. The circle itself represents the plot size or the plot area, and which seems to help identify where is the field exactly in the image. So using this annotation tool, we were able to annotate around 3,000 data points, and we split them for training and testing. We also provided the information about the annotation quality or the annotator confidence of the labels. So quality 1 means most confident, and quality 3 means it's the less confident samples. So after we collected and labeled the data set, we created a challenge and hosted on Zendi platform in order to allow data scientists in Africa and all around the world to contribute to this problem and provide models in order to have like an API in the future to be applied on all the data. So the winner solution was actually very interesting and diverse. So the first place solution was based on visual object detection models, and it used like only Planet Labs images. So it trained like YOLO 5 model on the annotations, and the solution had like transformed the plot area that we show in the annotation tool into a bounding box and trained the system on it. So this was the first place solution. The second place solution used an encoder-decoder convolutional neural network, where they created a probability field representing the probabilities that each pixel would be the target location. And when at the end or after training, the exact location of the field is taken as weighted median centroid using the probabilities as weights, and also used Planet Labs images only. For the third place solution, so they use like a direct regression model, also using CNN and Planet Labs, but they added like some augmentations like vertical and horizontal flip in order to increase the size of the data and improve the training results. So this was the final results in the leaderboard, and it seems like the first place solution were significantly better, with like at least 1 meter, but the overall the overall error, of course, it's still like in the 40 meter range, which hopefully we can improve in the future. So we after the end of the competition, we created a data set that contains the original data and the corrected fields using the labels that we made, and also using the predictions that the best model of the winning solution did, in order and applied also the model on not only the 3,000 points that we annotated, we extended the predictions to like thousands of other points, and hopefully it will like make an impact in other problems like yield estimation. So in the conclusion, the problem of field center detection still is a challenging problem. However, like the top solutions managed to produce deep learning models that improve upon the baseline. We think that in order to improve all these solutions, we will need to use satellite images with higher resolutions, hopefully with less than 1 meter, and also adding more annotations would really help make the model or help improve the final performance. So that's it. Thank you very much.
Thanks a lot, Karim. I have a really quick question. Is that data set available that you just described?
So,
could you maybe paste the link in the chat also? And maybe we can take another question here that just came in from Ahmed.
Sorry.
Sorry.
I couldn't see it on the chat. Yeah, go ahead. Yes, please.
Yes. No, there's another question from Ahmed. You can also ask it yourself, Ahmed. You're online.
Thank you, Patrick. So, Karim, I mean, in a smallholder dominated region, you have fields very close to each other. My question was, how did annotators decide on the correct field? Were there other metadata to be used, like area or something, other than the visual inspection?
Yes. So actually, on the data labeling tool that I was discussing, let me reshare it. Sorry for closing the share. So we depended mainly on the area. So if you look at the circles that we draw in the tool, it's quite obvious in this example that the only field that fits the area provided is the field, this field. So this was like a crucial information for the labeling. Also, we depended on the experience of CGI-AR agronomists in the region, so they had quite the experience of like how the fields look like and how can they correctly detect the fields. So yeah, mainly for the metadata is the plot area.
Thanks, Karim. I think we have to cut it off here.
Okay. Yeah.
The discussion can be maybe continued in the chat, but we have to move on to the last two presentations.
Sure. Thank you very much.
For the next presentation, we're moving a little bit towards the validation aspect and the use of reference data for validation, which is of equal importance, I think you will all agree. And this presentation is given by Konrad Bielski on best practices and methods for operational thematic map validation. Konrad, please go ahead.
Thanks, Patrick. Yeah, my name is Konrad Bielski with EU Explore. I'm joined with Heinz Gallum from Joanneum Research, who will sort of support me in case you have any questions. But we are definitely presenting within the context of the hotspot validation. But I would like to present this particular sort of presentation in the context of what we've been discussing here. So just to start off, I totally agree with what's been said before. We are in a golden age for Earth observation. I push that even further. We're in a golden age of map making. Literally, as we have seen, anybody and everyone with a few clicks of a button can create a map. And then the question then becomes, well, okay, who's going to be the user? How useful is that? And this is where I come back to the more maybe traditional context of map validation. We've been seeing a lot of great sort of confidence intervals, quality measures, but generally that's been produced by the producer themselves. And here, in the context of the hotspot map validation, the producer was very different, and the validators were also a totally different consortium. So this is something that actually, again, Patrick might come back to the funding and the new sort of ease approaches that you were suggesting, is the fact that we're still dealing with experts. AI is great, but so this is sort of coming from a more traditional perspective, but looking into the AI context, and especially thinking about how we're going to be moving forward with this. So again, if you want details of actually this particular framework, there's a paper out, and you can look at all the hotspot maps, including the validation reports, on the Copernicus website as well. So just to put the project into perspective, the objective was the validation of the hotspot maps. These maps were landscape level mapping. So the classes are a bit different again than what we're seeing here. And we're going to go through all the different steps in order to sort of just compare and contrast to, I think, Patrick, what you said in the beginning, the sort of computer vision domain and the geographer expert map maker domain. I think a lot of it is getting mixed up. I also think that at some point, the two domains will have to get together and decide, what does quality mean? What does confidence mean? All those types of terms are going to have to be described together and decided upon. So that's sort of the objective that I have with this presentation. And as you can see, the number of classes that were sort of requested by the map owner, which here is the commission, is quite varied. It's very different than what we've been seeing, sort of a more object-based identification and maybe identifying specific, we've been seeing a lot of agricultural samples here, which are doing very well and fit very nicely into the overall aspect. I'm sort of thinking here, from a European perspective, Green Deal. Yes, agriculture will be a part of that, but other land cover types as well, and other even objects will be required in order to understand sort of what's happening. And something also to be very aware about is our validation was very much not just the accuracy, overall accuracy of the map, but at the class level as well. That was very important for the map owners. So here you go. And again, just starting with a nice workflow. In general, the framework is based on 5 different components. Each of the components is independent. Each of the components is looking at a different part of the map and assessing the quality, not just for the information itself at the end, but also all to make sure that it's interoperable and all those other things that are necessary, especially in today's age of automation and sharing, etc. So the other thing I wanted to just mention is, if you look at this flow diagram from a computer software perspective, you can consider as a type of design principle. So these are the things that should be put into place when we're doing a validation, and they should be at the back of your head, or even very much defined when a validation is going to be generated for AI-based mapping. So just to start quickly, the first 2 components are, more document-based sort of validations. So A, has the producer delivered everything that was expected? And B, in component 2, is the metadata all there? Is the metadata using the correct terms? Is everything in line with expectations? I'm saying this, especially because we've seen so many projects, and of course interoperability has been a question. Can we start deciding about high-level metadata terms and codes, etc., maybe going into maybe ISO standards even, so that we can link the computer vision with the geographers and make sure everyone is speaking the same language. This is very important, especially when we start sharing data, both annotations as well as the final map results. Here's just a quick sort of maps that were generated, basically based on the component 2. So these are just looking at spatial accuracies, temporal consistencies, these are definitely valuable for this particular land cover type maps, especially because seasonality was part of the classification requirements. So now going into the next level of map validation, we all know the quantitative parts, the map the user and producer accuracy calculations. Generally we use some kind of statistical sampling, but we've all had this problem. You sort of see a map, you see that the quantitative sampling has been great, but as an expert, it's very easy then to look at that map and say, oh, but why wasn't it sampled there? Taking a theoretical sort of sampling approach is definitely needed for quantification, but a qualitative assessment is also necessary so that the experts can deliver to the users what they feel are the problem areas of the map and the final results. So the way this was achieved in our case, especially because it was a landscape level classification, the entire map product was assessed on a 10 by 10 grid, and for each grid, there was an assessment done in order to say, was there a problem there? Why was there a problem there? And as you can see, we had the two results. So one is the land cover result and one is the land cover change result. Just to be sure, in this case, any land cover results that were erroneous were not then used in the land cover change results, because then you would see sort of a doubling of the errors. So in the land cover change, the validation was only done on the change itself. But again, as you can see from a map perspective, this is, you can see generally the areas where, from a expert validation, the producers were having trouble with the classification. So this is again a good way of having an overview of the entire map, and from a usefulness perspective in the future, somebody who is using the map can say, okay, yeah, if I'm interested in this area, things were looking great. Otherwise, in these areas, well, I need to sort of pay attention to how my decisions are going to be based on that information or not. Now we get to the next level, and this is again the quantitative accuracy assessment. This is the one where most people are used to, where we provide the the errors per class. And just to sort of show you that depending on the class size, and here we're talking about area, there was different sampling requirements, and also in the land cover change maps, those requirements were also different. So if we consider the automated mapping from an AI perspective, these are very important things as well to take into account. And here we have just the sort of the flow of the quantitative assessment. Again, I suggest you go to the paper or the Copernicus website for details on there. And just one thing I wanted to mention here that is probably very relevant for annotations as we've been discussing. So the one thing is the blind interpretation, which is essentially where all users take a look at the same image, the same class, and make their decision. So what happens when you have differences in that interpretation? Well, then you need to get together somehow and make those final decisions to see, what will this be annotated as? And that's what that was part of this quantitative accuracy assessment. And the tool, which is very much similar to the ones that we've seen before as well, because these classes were landscape and fairly difficult to identify easily, because they took into account seasonality, different types of land cover as well. So this type of dashboard, which can be shared among all the validators, so it's not just a single person doing this. This is a very important way of working together. and as well, just to show the fact that, you know, it's not enough to have a single type of Earth observation image in order to make this decision. It's about, you know, access to data, you know, the different expertise, and of course, open source information is very valuable in these contexts as well. Not to go too much into the quantitative accuracy part, but you know, machine learning is great, and this type of statistical analysis is going to be very favorable when it comes to the validation of such data sets, because we can certainly take advantage of numbers. One just quick note on that is that we had applied bootstrapping rather than using, let's say, analytical equations, because it's far easier to adjust and much less problematic when it comes to calculations. This is especially relevant in the sampling and the area estimation. So conclusions. The main point I wanted to make is the fact that, you know, just making a map is the first step. What's very important once you make the map is to be able to provide the users with the trust they need in order to take advantage of that map, and then use that for either the decisions or their further information. So that's where this validation step is vital. It's both linked to not just the map making, but also the input data, as we're seeing here for the training. So that's validation is definitely a very important aspect of this. So again, the framework we've presented here, we believe is very much applicable to AI-based mapping. And so we do hope that that's going to be sort of made a part of some of these AI map productions. The other thing too is, as we're seeing, automation and distributed teams, this is a necessity. We have data sets from around the world. We need expertise from around the world. We have to have access not just to the teams, the automation. This is definitely a must. And as we're seeing from a lot of the other presentations, we are going in that direction. Just a final sort of thought, and that's, again, should an open access reference database be developed from, you know, machine learning applications? From our perspective, that's a resounding yes, because, you know, more maps means we're going to need a lot more information to be able to support that map making. So thank you very much, and I hope we can have a quick discussion about that after.
Thanks very much, Konrad. Unfortunately, due to the time, we cannot take questions now, but please do put questions directly to Konrad or in the chat box as well to all. Thanks a lot. It was very insightful, the presentation. With that, I would like to move to the next and the last presentation, actually, by Hamed. Hamed Ali Mohammed. That is the correct spelling of your name. Please tell us a bit more about the Radiant Earth activities you're having on the open access repository Radiant Earth has been building. Over to you, Hamed.
Thank you, Stefan and Patrick, for organizing this great session and having me here. I hope you see my slides now. Yeah? Okay, let me know if there was any problem. So yeah, as Stefan mentioned, I'm Hamed Al Mohammed with Radiant Earth Foundation, and I'm going to talk about Radiant ML Hub, which is an open access repository for particularly ML-ready EO data, and I will mention at the end what is the vision moving forward. A quick intro for those who may not be familiar with Radiant. We are a nonprofit organization, and the mission is really building an ecosystem of training data models and particularly standards that would empower users and organizations across the development sector to better use these open satellite data and AI technologies for addressing many global challenges, from agriculture, climate change, biodiversity issues, and so on. And really, the vision is to basically use the advancements in these two domains, ML and Earth observation, for global impact. What Radian does, if you look at the what I call a data ecosystem, is focusing on publication and uptake. You can think about data journey from a collection point to an impact point, but Radian as an open and a neutral organization really focuses on how we can better publish these data, particularly with the ML focus, and how to have a role in facilitating uptake so users have better access and better usability of that data. And what I will present today is focus on these two aspects. But we work closely with other organizations across this basically data journey, I would say. I mean, you probably have seen many elements of this figure today. Looking at an ML cycle, you start usually with a set of training data, you build a model, you deploy that and do some predictions, then you do some evaluation, whether it's a performance metric or doing some that we just heard in the previous presentation. And based on that, maybe another group comes, improves that training data set, and goes through this cycle. So we always learn through this cycle. And this is an iterative process. It is not a one-time thing that we do it, we get some performance metrics, and we are done. We're always improving in this cycle. But looking at this cycle, we still have some challenges, particularly when it comes to doing this in the earth sciences. And this figure is from an article we wrote about a year ago out of a workshop, expert workshop we hosted before the pandemic. The last workshop we had in person in 2020. You can see that in the AGO EOS, but we kind of summarize these challenges in three aspects. One is on the training data side. We need better benchmarks, particularly looking at other ways of populating this data ecosystem, maybe using synthetic training data. We also talked about model development, what we need to do there in terms of incorporating some of the other features, how we publish these, and particularly on documenting and sharing these. And this is where I want to touch base today about standards and repositories that would facilitate this data sharing and discovery, considering the requirements of an ML ecosystem, and also incentivizing this. It is not just an infrastructure, we need to also empower and incentivize developers. And if you look at the ML domain, particularly the computer vision domain, you see a lot of, I would say, high quality, well documented and well adopted benchmarks. I mean, ImageNet is the most famous one we all use, but there are many other ones there. And there are four common properties or characteristics among them if you go and study them. They are published in what we would call an ML ready format, which is if a user comes to use that data, they're using any programming language, usually Python, and they have an easy way of loading that data. They don't need to do too much of a processing or pre-processing to get the data into the programming environment, particularly if they want to use a TensorFlow or any other like ML packages. Whether it's using an adapter or it is already stored in that format, that is ready for the user. And that is a key property of adoption here. These data are well documented, so you can see the provenance, how they were come about. Even if they're crowdsourced, you see a lot of good properties documented there. They are regularly maintained, meaning that they are not just one data set. If there are issues and biases in the data, they regularly publish a new version to try to mitigate those. And then there's a good discussion about the train test split, that the benchmark usually has that train test split predefined. So if a user is building model against that, they can report their accuracy. So to address many of these challenges, that's what Radian established a couple of years ago as Radian ML Hub, to be an open access repository for geospatial training data, considering all the, again, properties that a geospatial data set needs. And beyond just the hub or the training data hub, we also work closely with the community. So Radian has been kind of convening the community to decide and to develop many of these guidelines and best practices, how to do this. If you're building a repository, what should we do? What should be the standard? What should be the specification? And we do this through these kind of convenings, and also doing some like technical working groups and workshops in addition to those convenings that are usually experts. And last but not least, doing education and training and tutorials. We do boot camps, we provide a lot of tutorials and online kind of webinar things, and also market information for the community to learn about the latest advancements in the community. But I'm going to focus on the hub today. And this is, for those who might be interested, what is happening behind the hub when you access it. So in terms of data storage, ML Hub is agnostic where the data sits. We currently use two cloud providers, AWS and Microsoft Azure, and the training data can literally sit in any cloud. The key aspect is to have a standard data catalog, which we use the stack. I will show in the next slide. And all of the data sets are kind of documented and the metadata is stored in a stack. And then there is a stack API and a dashboard for users to basically access the data. There is authentication, but it is open access, so anybody can sign up and get their basically authentication key. The reason for having that is honestly being able to report on the statistics, how much the data is being used, so we can basically provide better support. And how users access the data is through a public API. If you're interested to write your own code, there is a Python client library that you can use and easily search for the data and download them. And also there is a web portal on the mlhub.earth. I will show you in a screenshot how does that work. So it's basically, I would call a federated data store. It can sit anywhere. There's a set of standard catalogs and a standard API, which is based on the OGC API. Actually, the Stack API is compliant with OGC API. And there is open access points at the end. And these are all built on Stack. So Spatial Temporal Asset Catalog is a specification that Radian convened the community. We were just kind of leading the community to define this, but it has been more than about 25 organizations getting together the last 4 years to define how we would store our metadata for geospatial data sets. And one of the specifications is for ML training data sets, or generally labeled data sets, as I would call it. It is basically open access. It enables search and discovery, and it is based on a simple core definition and some extensions. If you have labeled data, if you have SAR data, or any other kind of specific data sets would have their own specific extension. And it's very much community driven if you're interested to see that. And version 1.0 was released earlier this year in July, and that's what Radian uses internally as well. This is a snapshot of what the datasets website look like. So you see a map of all the data sets that we have and kind of cards for each of those. You can filter them based on their keywords or dataset type. And when you land on a dataset page, you get all the properties of that from description, from the DOI, from a documentation, and also a code snippet, how to use that data within our Python client. You can also download the data right there. If you're interested to just download it and use it however you want to do internally, you can do that. You don't need to use necessarily a Python client, but there's all those access points to make it easy for users to access this. And it's community, so anybody can host their data sets. A quick snapshot of the dataset types we have. We have several crop type data sets, some series of buildings and roads detection, land cover classification, training data sets, and also natural disasters like fires and flood data sets. And what is next for us? So expanding on the training data catalog, but we're also thinking about model catalogs now. So if you look at this cycle of, again, ML development, you always do this machine learning development, you do some exploration, analysis, you do, again, more feature engineering, and you do this cycle again and again to improve the model. So we need to catalog our models to record and capture these processes. And that's what is missing now in the community. And that's what we have started in the last 6 months, which is a geospatial machine learning model catalog. So what are those metadata that you would need to catalog a model and publish it for the public access to make sure there is a provenance, there is reproducibility, and there is also easy discovery and search. Because if you need a land cover model, where should you go and search for that? So that's what we envision. A series of federated stores of data. It is not going to be just ML Hub, but a series of those that are interoperable, storing both training data sets and models that would basically facilitate easy access for users and publishers of those training data and models. And we welcome any contribution or collaboration from other organizations who would be interested to work in this interoperable ecosystem. With that, I would be happy to take any questions. We also have a Slack channel. I will put the link in the chat, which is a community channel. People chat about training data and ML topics. If you're interested, you can join there. Thank you.
Thanks a lot, Hamid. Great to have you, and especially, to make everyone aware that you actually are willing to present here at 5:30 local time where you are. So much appreciated. And always great to see the progress that Radiant Earth is making here with a few really good ideas. we are running out of time a little bit because we have to close at 12. But I was just wondering, you know, with the ML repository or the catalog of ML models, you know, I mean, quality assurance for the input training data sets is one thing, but then trusting a pre-trained model in terms of the, you know, how much attention was paid to detail and quality of what went in there. That's a whole nother topic that we probably don't have time to discuss now. I think Sarah is going to take over now with the live polling of the questions that we had prepared.
Yes, you can find on the chat the link where you can connect with your phone or with your computer, and you have 5 questions. And you just need to go there and select one of the choices. I wonder if we can see how many people have voted already. I think at the moment we are around 53 participants, but I don't know if we can check. I'm gonna unshare the screen just to see if I can see how many people have voted already. No, we cannot see, but I suggest we leave it for 1 minute maximum for everyone to vote.
So maybe if everybody who is in the current session could go to this Phi-week poll.
Yes.
It's pasted in the chat box for those who don't have it open.
Yes.
That would be great. Yes, thank you.
Okay, so this tool is GDPR compliant, but it doesn't allow you to browse through the different questions we have in there. So we have to do that together. So everyone's kind of asked to answer the first question here. And then we will move to the second one. Wait another.
Okay, so I will move to the next question. Is it okay?
I think so. Can we review the results after
Yes.
going through the questions?
Okay.
Yes. Okay, thank you.
So for now, almost half will vote increasing the data offering, followed by quality assurance for training reference data, and then making fair compliant data, and finally only 12% open data engineering tools.
Maybe we can, yeah, Sarah, maybe you move to the second question. We can discuss that a little bit, because I saw that in the presentations provided by Konrad and also from the World Cover, that there was quite a bit on different quality indicators, so thematic, geometric, and temporal consistency indicators. And I was just wondering if any of those are automatically computed or if they are all kind of manual queries to the data creator.
Patrick, I can quickly answer that. Some at this point are automated, some are not, but can be. And I think that's the important thing is ideally in this context, it has to be automated. But then it comes back again to quality and trust of the inputs to sort of take advantage of that from a validation perspective. Yeah. And again, you know, is it okay to use the producer's data to validate their own products, or do we need to have separate data sets to do that as well?
Good point. Yeah. And also, I mean, that's the one thing that the IASA tools are doing quite nicely, you know, looking at multiple votes and only considering something reliable if you have at least 5 responses to an interpretation. Okay, so that's for the second question here, we see a clear tendency too that in terms of open data engineering tools, so tools for training data creation are obviously the most important ones, closely followed by those for training data optimization. And Hamed, a question to you. Are you already considering these kind of things? The second point there, the training data optimization part?
We have done this on like dataset level, but not as a service yet. It's kind of a R&D level, but it is definitely an issue, and I'm happy to see that everybody agrees with that as a high priority thing. But yeah, we have done it for some sample datasets like land cover net that we use And we did something similar to the consensus algorithm that I think Stefan has presented earlier, that if you have multiple users looking at the same data, how you would optimize your data sampling, basically. Yeah, land cover net, I can share the paper in the chat. We did something related to that.
So maybe I'll move to the next one because
go ahead. It's quite interesting that the tools for model training and parameterization are so little required. So that's interesting. So everyone's okay with the resources they have at hand for training and parameterizing their models. That's interesting. So the third question here is basically an open text question. You know, should we think of a similar model for, you know, providing European funding for coordinated reference data collection campaigns, similar to what Lacuna Fund is doing? And well, I realize that we're running out of time here for a free text response, but we should have probably gone for pre-existing answers here. But I think it is, in a way, the next logical step. And I think if we all come together again at the LPS and, you know, maybe we can already then in May discuss some potential avenues to fund data collection campaigns together. Stefan, any thoughts from your side?
Yeah, no, I mean, maybe it's time a little bit to wrap up. We're very close, right, to closing this, and I think we've had some very interesting talks in all the sessions. It was really tight, so unfortunately we didn't have too much time to ask questions, but a lot of questions have been posed in the chat and have been answered. And I think this is a continuous topic which will not go away from us. And as you have already outlined kindly, Patrick, there's the opportunity also at the Living Planet Symposium just to remind people that this will be taken up again. And I think globally, lots of other institutions are understanding and recognizing the importance of in situ data or on the availability of in situ data. And I'm sure this will not be the last meeting we will have on this topic. I would just like to thank all the presenters for some very nice and interesting presentations which have been made. And thank you very much from my side and from the IASA side. And maybe you will have the final word, Patrick. Over to you then.
No, I thought this was a really interesting workshop with, you know, really a great set of presentations. You know, as we said multiple times, we would like to continue this discussion at the Living Planet Symposium in Bonn in May, where we will organize some open for Agora sessions and some science sessions on this topic. So thank you all for attending, and thanks for providing some feedback here in the live polling. We were a little bit short on time, but still there's really interesting implications here in your responses and everything. So so thanks to all the presenters. Thanks for Sarah for supporting us with the live polling. And this was a really enjoyable session. Thanks, everyone. Have a good day.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye-bye.